achieve that if you put here a log of lambda squared, integral d lambda squared over lambda squared times log of lambda squared generates the double pole. Yeah. No. We don't. So this we would like to preserve this general form, but we have to admit that this is not anymore an anomalous dimension, and it would depend explicitly on the scale lambda squared. Now, what I would like to explain in a few words is the motivation behind this formula here that is written for the anomalous dimension gamma. So the statement is, first of all, that up to 2 loops, all the singularities of massless scattering amplitudes are summarized by this extremely simple formula. You just take that function here, plug it into this exponent, integrate over lambda, use the d-dimensional coupling here inside these 2 anomalous dimensions, and we generate all the singularities in any massless gauge theory amplitudes, and that's a completely general result up to 2 loops. Okay? What is the structure of this dipole formula? So we see here 2 terms. There is the first term here that's proportional to the cusp anomalous dimension, where I extracted out the Casimir, right? Casimir out of the quadratic Casimir that this cusp anomalous dimension normally is proportional to, and removed it because the color factor is taken into account here. And I sum over all the color dipoles that are formed by pair of partons I and j. For each one of them, there is a log of lambda squared over the invariant mass corresponding to the Sij pair. And that term alone gives all the double poles related to collinear singularities and all the non-trivial content of the soft matrix up to 2 loops. So including single poles that are generated by Ti dot j, which is a color dipole. What we see here in addition is Harald collinear singularities are generated by this field anomalous dimension associated with a particular jet in one of these directions. And then we have to sum over all jets. So that's basically the structure that we see. You see this structure at 1 loop, that's completely natural. Why does this structure appear at 2 loops, and why it was proposed as a potential formula to all loops, I will discuss next. So this was proposed in 2009 based on explicit calculations that were done 3 years before, confirming that this is indeed the most general structure that you get, and there is a long history of that going back to the Atomic paper in '98. So why was this considered a potential ansatz for the singularities beyond 2 loops? And also, why is there nothing new that occurs at 2 loops? And at 2 loops, in contrast to 1 loop, you can, in principle, correlate between 3 partons simultaneously, Ti, Tj, Tk. Okay? And generate some correlation between the 3, perhaps involving momentum dependence of the 3. So to understand why this doesn't occur and why this was then proposed as a generalization, we need to recall the structure of factorization and the scaling symmetry property. So first of all, we are considering fixed angle scattering as before, but now we require strictly that Pi squared is right-hand. So this beta I squared are light lag. Now we do not form these gamma ij, which are the rescaling invariant kinematic variables associated with these cusps in the Wilson lines. Instead, all we have is beta I or beta j. So if we define the correlate of Wilson lines with light lag Wilson lines, the only thing on which it can depend is this beta I or beta j. And that violates the rescaling symmetry. Yeah. Yeah. Okay. So I'll have to hurry up a bit. This would violate the rescaling symmetry if we have that dependence. Now, obviously, we cannot violate the rescaling symmetry. We cannot and there cannot be dependence on the actual velocity that we use to normalize our Wilson lines for the amplitude. So what can it cancel against in this formula that will come next that I'd like to explain. What you see here is a factorization formula of the amplitude for the light lag case. The part that we have seen before has a soft factor times a hard factor, so that is exactly the same as what we have in the non-light lag case. And what happens, in addition, is that we get these jet factors that correspond to collinear singularities. This J includes particular hard collinear singularities do depend on the spin of the emitter. And you see that I divided here for each jet by the iconal jet function. So for each jet that I included, I also subtract something, I also divide by something. What is that? These are the soft regions that are in overlap between the jet and the soft. So the jet includes this overlap between soft and collinear region. So because both soft and collinear with one of the jets, they are taken into account in this jet, but they are also taken into account in the soft function that makes the correlate of all that depends on all soft gluons, and therefore there is an overlap and I have to remove it. Now, so this is the consistent factorization formula, and now you see the way in which this rescaling symmetry can be saved. It is this iconal jet here that saves the day, that allows to remove the dependence on the normalization of the velocity beta that happens here. Now this is very important, that this rescaling symmetry violation is cancelled by this simple jet factor, or rather by the product of these jet factors. It is important because these jet factors are very simple. Each one of them depends only on one direction, and they are followed singlet objects. And therefore, if they help to remove this dependence on the normalization of the beta from the soft function, it must imply that the soft function itself has a very simple structure, at least in as far as this normalization dependence is concerned. So there is a constraint on the soft function itself by the fact that the normalization dependence cancels with these very simple objects, which are total singlet. So this complicated object, which depends on the correlation between color and kinematics of all the process, obeys a certain constraint in relating it to this jet factor. And that was the origin of the dipole formula. We set up constraints that hold to all orders, and the simplest solution of these constraints was the sum of the dipole formula that I've already shown you before. This formula here is the solution of this set of constraints, and that is basically the explanation why it was proposed. And similarly, you can understand that a term with a Ti, Tj, and Tk would introduce dependence on the momenta, which is inconsistent with the scaling symmetry. That's essentially the reason it doesn't appear. It's very easy to understand it from this perspective, but it's not the way it was today. So as soon as we wrote down these constraints and we had the solution, we also realized that there is a way to bypass this, namely there are contributions that could appear that would be complicated and would not be directly, would basically bypass the rescaling symmetry constraint. How do we bypass it? By forming some function which is by itself invariant with regards to rescaling. So the potential, the first corrections, potential corrections to a dipole formula that could occur are these corrections that I will discuss next, that depend on conformally invariant cross ratios like this. And you see here that if I rescale pi by some number, that would cancel out, and similarly for the other ones. So this quantity lives on its own in the soft function and does not correlate with the jets, and therefore I can say nothing about it except the fact that it depends on these conformally invariant cross ratios by looking at the factorization. It turns out that this type of corrections to the dipole formula are highly constrained by a set of different considerations. Some of them are already mentioned. The fact that there is going to be an exponentiation, namely that the exponent contains connected color factors only, that tells you that basically at 3 loops, the color structure of what we are introducing must be this plus permutation, nothing else. And then by Bose symmetry, once you know that this is the color structure, you know that the kinematic dependence must mirror the permutation symmetry of that is present here. So that highly constrains again the kinematic dependence of this function delta. We also know that these corrections that we're looking for here at 3 loops, they would have uniform weight 5. Why do we know that? These corrections are the same in any gauge theory. Now, the same in any gauge theory because the matter content does not enter at this point. And therefore, we expect, based on our familiarity with n equals 4, that it would be maximal uniform weight 5. And finally, there are the collinear limit and the RECCE limit, which are interesting kinematic limits when we know extra properties of the amplitude, and we can see what this implies with regards to this function delta, which is defined in general kinematics. So I see that I'm very short on time. I will briefly mention what this slide refers to without getting into too much detail. What you see here is a summary of the state of the art of the different contributions, basically separating between the massless case and the massive case. We are now in a situation where for the massless scattering, we essentially know everything at 3 loops, apart from a small detail that I can mention at the end. We essentially have everything in 3-loop order, soft numbers dimension, know at 3-loop order. And what I would like to report last is precisely this calculation at 3 loops. For the massive case, the situation is, of course, more complicated. When the distribution lines are not light-like, there are many more contributions that can occur. It's complicated already at 2 loops, but at 3 loops, it is very complicated. And Wilson line, when we have 3 or 4 Wilson lines, there is no full answer. We only know certain contributions. The Caspar normal dimension itself is known to 3 loops, but this is again the new result from this loop. Okay, so coming now to the actual calculation that is new, let us look at the classes of diagrams that contribute at 3 loops that correlate between 4 Wilson lines. So these are all of the diagrams, all the classes of diagrams that correlate between 4 Wilson lines. I separated them further into the ones that are the single connected graphs and the other. here are 2 separate pieces, and here are 3 separate pieces. And this separation is motivated by the fact that these 2 depend on all of the 6 angles that you can form between these 4 Wilson lines. Whereas these, they depend only on the subset, here 4 and here 3, but you can never form a conformally invariant cross ratios here or here. So if you go to the light-light limit, where these velocities beta I go very close to the light cone, what you can get here out of these diagrams are only sum of products of logs of these gamma ij variables. Very simple answer. You cannot get cross ratios from that. And similarly, if you look at diagrams that connect fewer Wilson lines, you can only give sum of products of logs in this limit. But these diagrams, they depend on sufficiently large number of angles that they can give by themselves functions of conformal invariant cross ratios, and these are the ones we actually compute, and that is the last calculation that I would like to report upon. That was finished basically this summer. So this is the easier diagram of the 2. I will be very brief about how we have done that, given that the time is very short now. So what we see here is that we have done the calculation in configuration space. Here there is a single point to integrate over in d dimensions, and the rest are parameter integrals of these attachment points where the gluons are emitted, going from 0 to infinity. These are just parameter integrals along the Wilson lines. What we did is we mapped it in the first instance to this integration over z into an auxiliary momentum space, where the momenta are defined by the differences between the coordinates xi. So this is similar but the reverse of what Marcel showed earlier. We are now looking at an auxiliary momentum space picture, and this is a 4-mass box integral that is equivalent to integrating over this position z. Once we have this box, all we have to do is to perform the integral over the Wilson line variables. But we realize one simplification is that when we consider this integral, there is only one singularity that can be generated. And this is when this entire web gets very near the origin. This entire web can be scaled, and that would give a UV singularity. But there are no other UV singularities. There are no subdivergences. So that means that once we extract the singularities by scaling all the variables, we have 1 over epsilon times a finite integral we can evaluate in 4 dimensions. And that simplifies the calculation a lot. And now I'll not discuss in great detail what we have done. There's a similar picture for the other diagram, but here it's a 2-loop integral that you get in this auxiliary momentum space that represents the integral that we see here in configuration space. And the point is that these are very difficult integrals to perform if you want to evaluate analytically also the integrals over these Wilson line velocities. So the way we dealt with that is that we considered the asymptotic light-like limit. And then we used the Mellin-Barnes techniques in order to extract the leading term in this asymptotic limit where the Wilson line velocities are almost light-like. So what can the result depend upon in this asymptotic limit? It can depend upon these variables that get very large, these gamma ij, because the beta I squared are nearly 0. And it can also depend on these cross ratios that are finite. And this is the non-trivial dependence on these cross ratios. So asymptotically, we extracted, using the Mellin-Barnes techniques, the result that reduced the number of Mellin-Barnes integrals that you have very significantly from something like 14 to 3. And then we could use techniques of basically mapping it back to parameter integrals and using polylog techniques in order to write this as known polylogarithmic functions, and the answer is written in terms of polylogs. Before I get to the answer, let let me explain what variables we write the result in terms of. This is exactly the same variables that we have seen in the previous talk. The conformal invariant cross ratios are then expressed in terms of Z and Z bar as shown here. So these Z and Z bar are algebraic functions of these conformal invariant cross ratios, and the polylogs that you get at the end are functions of these Z and Z bar variables. It's interesting to look at how Gauss symmetry is realized. This is shown in this diagram. I'll not go into details, but what you basically see is that permutation symmetry corresponds to a transformation such as Z to 1 minus Z in the kinematics, or Z to 1 over Z, depending on which permutation you are making. So if we look at this 4 gluon vertex diagram, the permutation symmetry is all realized at the level of the Feynman rule, essentially, and it's very simple. You see that this factor in the brackets over this Z minus Z bar realize Bose symmetry. So this function G1 is a function that is by itself Bose symmetric. It transforms trivially under all these permutations, which is very nice. Now, combining the results, we have to take this diagram together with the other three. The other three are more complicated. At least in one sense, the result is significantly more complicated. It involves not a single function with an overall rational prefactor, but two different functions that are polylogarithmic that involve different rational prefactors. One, it doesn't have any rational prefactor, the other one does have. And the interesting thing is that the most complicated beast in this business cancels when we sum up all these diagrams. So it's almost this zero that some people anticipated that this would give. There is actually a very massive cancellation when you consider this gauge invariant object that you obtain when you sum these diagrams, and the terms that have these rational prefactors cancel. You remain only with these terms that do not have rational prefactors and are pure functions of weight 5. And that is very good, because that is what we expect on general grounds, that the result that is valid in n equals 4 should have. Should not have some mixed structure like that. And this function, G0, is a function that again has very nice symmetry properties. Its symbol is composed of these letters, and its singularities can be understood as singularities that are related to the different RECCE limits that one can take when considering these 4 particles. So let me return here and explain how we got the final answer based on this calculation. So this is the last complicated thing to explain. So far I told you that we computed specific diagrams, just certain diagrams. If I use the Jacobi identity and sum up the diagrams that we computed, these connected graphs, I get this structure here. I got rid of one of the 3 color factors, and I remain with 2 functions here that are related by permutation. And now I would like to get to the full quadrupole correction, the correction to the soft anomalous dimension, the physical object. Now, there are some diagrams that we didn't take into account. How do we proceed? The point is that here there is a nice observation. Once we have used this Jacobi identity, this function, f1 and f2, they themselves factorize, or not factorize, separate into a sum of 2 terms, that one of which depends on these non-trivial conformal invariant cross ratios through C and Z bar, and the other depends on these variables that get large when we go away from the, go towards the light pole. There is this separation. Now, rescaling symmetry tells us that the final answer can only depend on C and Z bar. It cannot depend on that. That would violate the scaling symmetry. So what it tells you is that this part here should go away when you combine this result with the other simpler diagrams that we have not computed here, and that's indeed what happens. But there is a subtlety, and the subtlety is that there is a little bit of ambiguity in separating these terms. I said that they separate, but if you take a term which is very simple, that is a sum of products of logs, just logs of the conformal and transpose ratios, you can either put it here and write it in terms of the gammas, or put it here and write it in terms of CNC bar. How to resolve this ambiguity was the last thing that we had to solve. And here comes to help the RECCE limit, where we know how the amplitude looks in a particular kinematic limit. And we can use that in order to infer which of these simple logarithmic terms can appear in the final answer and which does not. And that, with this, I will finish. Let me just say in one word what we do here in the RECCE limit. The RECCE limit, we know what happens when the invariant mass is much larger than the momentum transfer. In this case, the trajectory that is captured by this alpha of t here is fully captured by the dipole formula itself. So this quadruple correction cannot contribute to the RECCE limit at leading and next to leading logarithmic accuracy. And therefore, at that level, we can know that leading logs and next to leading logs cannot emerge out of this delta that we computed. It must contribute 0 in this particular kinematic limit to leading log and next to leading log, and that's how we resolve that ambiguity that I explained. And here is the final expression that we got. You already know about this single value harmonic polylogarithm, so I'll not extend on this discussion, but you see how simple the result is when expressed in terms of this right class of functions. And precisely as in the previous talk, the reason that these are the right functions is that we should not have any singularities in the Euclidean region. So these are single values, precisely telling us that there are no singularities in this region where Z and Z bar are complex conjugate of each other, which lends itself to this very simple expression here for this quadruple correction to the soft singularities at 3 loops. So now there is a very interesting aspect to still discuss, but I will finish with a celebration that this ended a bet that it took quite some time to resolve between our chairman and Lorenzo Mania. So Lance got this bottle of Barolo for winning the bet against Lorenzo. Basically, the bet was whether or not there are corrections at 3 loops that go beyond the dipole formula, and now we know there are, and the formula is written on the board, so when it was revealed, then Lance got this bottle of Barolo, and I'll just finish without mentioning the one that did the work. It is not finished. So what is really in the center of this work is the investment of Oyvind Almede. Basically, his PhD was to do these integrals, difficult integrals that I explained before, involving a huge amount of computer algebra, very sophisticated manipulations, and it took quite some time. So let me move on to the conclusions. I will just mention the part that I did not have time to is extremely interesting. This is again the discussion of the collinear limits that we have seen as an interesting limit before. Also in this case, there is a potential violation of collinear factorization, which emerges as a new phenomenon at 3 loops. It's a different phenomenon that occurs for the first time at 3 loops.